Bismillahirrahmanirrahim. How are you, students? Today we will study unit number 8, waves, lecture number 34. Today topic is mechanical wave. Mechanical waves is a wave that is an oscillation of matter and therefore transfer energy through a medium. While waves can move over long distances, the movement of the medium of transmission, the material, is limited. Therefore, the oscillating material does not move far from its equilibrium position. Now, we will go into detail of this topic. Here we look at the given examples. It's before collision. Waves is produced in this direction, traveling in this direction. Here, medium is changing. Medium is changing. This is denser medium. This is rare medium. So, when it reflects from a denser medium, crest is converted into trough. Crest is converted into trough. So a phase change of 180 degree will take place. So when a ray traveling from rare medium and reflection take place from a denser medium, a phase change of 180 degree will take place. Now if you look to the second example, here before collision wave is traveling in denser medium, and here reflection is taking place from rare medium, so no phase change will take place. No phase change will take place. First condition is if a wave is traveling in a rare medium and reflection take place from a denser medium, phase change of 180 degree will take place. If traveling in a denser medium and reflection take place from a rare medium, no phase change will take place. Now look at the given example. Here wave is traveling in a rare medium. Reflection take place from a denser medium. Phase change of 180, no phase change will take place. Now in this case, reflection take place from a rare medium. So when reflection take place from a rare medium, there will be no phase change. There will be a phase change of 180 degree. Here phase change is 180 degree. So reflection is from denser medium. So when a reflection take place from a rare medium, no phase change take place. When it take from denser medium, a phase change of 180 degree will take place. Now reflection of sound. Reflection of sound is the phenomena of sound waves in which sound waves bouncing back after striking a rigid smooth surface. This is called echo. In a small room, when a person speaks, the sound spread in all directions. This sound can be heard by the listener in two ways: directly through reflection. You can hear directly, you can hear through reflection. It is difficult to distinguish between both sounds as it travels at high speed. These These two sounds can be heard distinctly if they reach or air at an interval of at least 0.1 second or 1/10 of a second. If the gap in it you hear after 0.1 second with a gap of 0.1 second, you can differentiate. The characteristic property of human ear due to which it cannot distinguish between two sounds if they reach the air within an interval of 0.1 second is known as persistence of hearing. Now you can see in the given diagram here reflection take place from nearby wall, so it is called reverberation. It is reverberation. It is reverberation. Reverberation. And here reflection take place from far distances, so it is called echo. So in echo, sound is reflected from far places, reflected from far places, here from nearby wall. Now echo, this is echo. If you sound travel in this direction and bouncing back into the same source, echo is the reflection of sound which you hear after when you produce the sound. Now stationary waves, the most important topic of this chapter. Stationary waves are produced by superposition of two progressive waves of equal amplitude. Amplitude is what? Is equal. Frequency and frequency. Frequency is equal. Traveling in opposite direction. Direction is opposite. So this wave is traveling in this direction and it is traveling in this direction. This is called stationary waves. As a result, no wave will be produced. Now standing waves. The length is L, fixed at this end and also fixed here. If you plug it at the middle, plugged at the middle, one loop is produced. Stationary waves, one loop is produced of stationary waves when two plane waves having the same amplitude and frequency traveling with the same speed in opposite direction along a line are superposed. A wave obtained is called stationary waves or standing waves. Here in this loop, one loop, this loop is equal to 1/2 of wavelength, half of wavelength. Plug the string in the middle, it will vibrate. Wavelength, the picture is twice the length. Now in this case this is equal to L, so L is equal to lambda by 2. Wavelength will be 2 times of length, 2 times of length. Now we will derive the different relation for one loop and then we generalize the relation. Transverse stationary waves in a string. Now we know that V is equal to F lambda. In this case lambda is equal to 2L. So V is equal to F into 2L. Frequency is equal to V by 2L. This is the frequency of this wave. frequency of this wave. Now consider a general relation. This is if we produce two loops, the length is same, L is equal to lambda. Frequency in this case is A prime, V is equal to F lambda. Wavelength changes, frequency changes. F prime, lambda prime. So in place of lambda we will write L. We'll write again. In place of write V, A prime and L. So F prime is equal to V by L. So write 2V divided by 2L. F prime is equal to 2 F1. Now we will do these calculation for transverse waves, transverse stationary waves in a straight string. But before going into detail, now stationary waves. When two identical waves move along a string in opposite direction, they produce stationary waves. These stationary waves are the result of superposition of waves, either constructive or destructive. Here wave crest is produced, crest is produced. Here interact and they reproduce itself in opposite direction. Here destructive interference take place and then regenerate, the waves regenerate itself. Now if you can see in the diagram, when you plug at its middle, if you plug the string at the middle, one loop is produced. So in this case L is equal to lambda by 2. One loop represents half of wavelength, so lambda is equal to 2L. As we know that V is equal to F lambda, V is equal to F lambda. This is first case, so I will write F1. F1 is equal to V by lambda 1, first case. In first case lambda 1 is equal to 2L from the diagram. So F1 will be equal to V divided by 2L. V divided by 2L. Now as we know that V is equal to T cross L divided by M under root T cross L divided by M. If 1 is equal to V divided by 2L, so write 1 divided by 2L under root T by M. L in this case is equal to 1, so here we write T by M. Now per second loop, L is equal to lambda, second case, so lambda 2 is equal to this. V is equal to F lambda, lambda 2 F2. F2 is equal to V by lambda 2, V by L. So F2 is equal to 2 V divided by L, 2 multiply by 2 divided by 2, write 2 V divided by 2L. Put the value of V. F2 is equal to 2 into F1. This is equal to F1. Now see the third case. In this case, lambda is equal to lambda by 2 plus lambda by 2 one loop represents lambda by 2 plus lambda by 2, it is equal to 2 3 lambda. So f is equal to v by lambda. Third case, so write third is equal to, here lambda is equal to 2l divided by 3, v divided by 2l divided by 3 is equal to 3 into v by 2l. So f3 is equal to 3 into f1. So in generalized form we will write we will write that fn is equal to nf1, where f1 is equal to v divided by 2l or under root t by m 1 divided by 2l. Both equation you can write both the equation. Fn is equal to n divided by 2l under root t by m. Now the next thing is fundamental and overtone vibration. Overtone vibration. The lowest characteristic frequency of vibration f1 is called the fundamental frequency. f1 is equal to v by 2l is equal to 1 divided by 2l under root t by m is called fundamental frequency or first overtone. Fundamental frequency, this is called fundamental frequency or first overtone. First overtone. Frequency f2, which is equal to 2 f1, is called second harmonic frequency or second overtone. So from this we can say that this phenomena is known as the quantization of frequency. So in this string one loop is produced. So frequency f1 will be equal to v divided by 2l is called first harmonic. Here two loops is produced, so f2 is equal to 2 f1 called second harmonic, and this is called third harmonic. So students, stationary waves are the result of superposition of two waves having same frequency, same amplitude, and traveling in the opposite direction. Here, for one loop, wavelength will be equal to this. In this case, L is equal to one loop. Relation for frequency is this: f naught is equal to v divided by 2l. And fundamental frequency or first harmonic. Here two loops is produced. Two loops is produced. So wavelength lambda 1 is equal to 2L lambda L1 is equal to L. This frequency is called second harmonic. Here three loops are produced. So final relation for wavelength is lambda 2 is equal to L by 2L divided by 3. So L is equal to 3 lambda 2 divided by 2. This is called third harmonic, second overtone and third harmonic. This is the relation for wavelength, frequency, first harmonic, second harmonic, third, fourth harmonic. Wavelength is equal to, for two loops it will be equal to lambda 2 will be equal to L if 2 is equal to 2 upon, if 3 is equal to 3 upon, if 4 is equal to 4 upon, and Fn is equal to Nf1. Thank you students. Allah Hafiz.